Welcome Math 107 students to the class activity Modeling with Systems of Linear Equations, lesson number 6. So the first problem we're going to look at is what we call a break-even analysis. And many applications in various disciplines involve finding the intersection point of two graphs, which is the solution to a system of linear equations. A common application from business is called a break-even analysis. Again, I just want to mention that it's a solution. This intersection point is a solution to a system of linear equations, assumes that both graphs are straight lines. So let's move on. For example, to launch a new product, a company often is required to make a substantial initial investment. So the company has to then begin to produce and sell enough units to offset that initial cost. So not only the initial cost, but then the cost of producing whatever item they're producing. So they want the revenue that they take in to offset the total cost and then start producing more revenue instead of cost so that they then make what we call a profit. So when this occurs, when the company has produced and sold the number of items so that the total revenue offsets the total cost, we call this the break-even point. So let's work through the following example, and we'll apply what we know about linear systems to determine the break-even point and do a break-even analysis. So we have a technology that's promising to bring light, fast, and beautiful wheelchairs to millions of wheelchair users. A company is planning to manufacture these radically different wheelchairs. Fixed costs will be $500,000, and it will cost $400 to produce each wheelchair. And each wheelchair will be sold for $600. So we want to work through the steps below to find out how many wheelchairs must the company produce and then sell so that they break even. And again, remember, what does break even mean? It means when the total cost is equal to the total revenue. And if revenue is a new word for you, it would be how much money the company actually brings in for selling the wheelchairs. So if they sold 100 wheelchairs at $600 each, then the revenue would be $60,000. Okay, so you just multiply the price per wheelchair times the number of wheelchairs, and that gives you your revenue. Cost is done similarly. The cost for each wheelchair times 100. So 400 times 100. But don't forget, you have to also include, if we're looking at total cost, that initial capital investment of $500,000. So right now you can see if they only sold 100 wheelchairs, their cost would be greater, much greater than their revenue. Okay, so let's define the variable of interest in this problem. Use both a quantity word and a unit word. So we're interested in finding out the number of wheelchairs the company has to produce and sell. So the number is the quantity of wheelchairs is our units. Wheelchairs is the units. That must be made, or you could use the word produced and sold. Okay, that's what we're interested in finding, the number of wheelchairs the company must make and sell so their total cost is equal to their total revenue. Okay, so now that we have our variable defined and we know what we're looking for, we want to write an equation that models the cost of producing those X number of wheelchairs and an equation that models the revenue from the sale of those X wheelchairs. Now look up here, we just picked a random number of 100 and figured out what the cost and revenue would be. So it's exactly the same strategy, except for now, instead of plugging in a specific number, we'll use X, which is the unknown number of wheelchairs. So we're going to let y represent both the cost and the revenue in dollars. So both equations will be of the form y equals. So for the cost, y equals the initial investment of $500,000 plus the initial cost of producing X number of wheelchairs when it's $400 per wheelchair. Now, I'm just going to make a little change to those instructions. I always like putting a little subscript to say, this is Y, so I'm following the instructions, but I put a little subscript C, so I know that this is my cost equation. Similarly, Y equals $600 per wheelchair to sell times the number of wheelchairs. And I'm just going to put a little R there. And that way it just is easier for me to see what each of these equations represent. So write and solve a system of linear equations to determine the break-even point. So we're trying to find the break-even point. So that's going to be when YC equals YR. So right now our system looks like this. Y equals 500. So if I go back and I take off the C so you can see why we gave you those instructions. Y equals. You're trying to figure out when the cost, which is 500,000 plus 400x, and the revenue, 600x, are equal. So this is your system. Here's your system of two equations. And so we want to know when are these two equations equal? So basically, you're going to substitute one of these equations for y. Let's say y equals 600x. I'm going to put that right there. Or another way to think about it is the idea I started to tell you about, which involves the same mathematics. When does YC equal Y sub R? When does the cost equal the revenue? Total cost equal the total revenue. So we have 600x is our total cost, our total revenue, and 500,000 plus 400x is our total cost. So there is our single linear equation once we've substituted in for the y, 600x. And now we solve this by subtracting 400x from each side. So 500,000 equals 200x. And now we divide both sides by 200 and we get 2,500. So remember, a solution to a system has two coordinates because it's a point, right? It's a point where they intersect. So if these were our two equations, we've now found the x value, the number of wheelchairs. We still have to find the output, or the y value, which is the cost, the total cost and the total revenue, which is exactly the same. So we have to go back to one of our original equations. Let's pick on the revenue equation, since that's a simpler equation, and put 2,500 in. So the y value when the x value is 2,500, let's see what that's going to be. So we have 600 times 2,500 equals 1,500,000. So equals 1,500,000. So the intersection point has two coordinates. Each of these coordinates represent two different amounts. This 2,500 represents the number of wheelchairs that is both made and then sold, and this represents the money that it costs to make those 2,500 wheelchairs, and also the revenue from selling 2,500 wheelchairs. So that's their intersection point. That's their break-even point. So when you describe what a break-even point means, and you can also check this by putting 2,500 up here into your cost equation, and you better come out with exactly the same amount of money, 1,500,000, or else you've made a mistake. So that's one way to check yourself. Okay. So let's describe what this break-even point means in the context of the problem. Do not write a generic sentence. In other words, I don't want you saying, oh, when you break even, your profit is zero, or your cost is equal to your revenue. Just like when we were doing our project number 1 and we were looking at our models and we found a point, whether that was an intercept or a point that told us the tuition and fees after so many years, you want to describe what each of these coordinates represent in a sentence. So in this case, when you write an explanation or when you interpret a break-even point, you want to say somewhere in your sentence what this $1,500,000 represents and what the 2,500 wheelchairs represent. And you can say it in different ways, but you want to make sure that somewhere in this problem you mention that the cost and the revenue are equal. That's critical. And what is the cost and revenue equal to? 1,500,000. And when does this occur? It occurs when there's 2,500 wheelchairs. So however you want to write that sentence, feel free. So let's do it. This is one way to write it. So what this means is that when the company, I'm just starting with the first number here, the 2,500. So when the company makes and sells 2,500 wheelchairs, the total cost and revenue will both be $1,500,000. That's what it means. That's what that break-even point means. Okay, so stay away from generic sentences. Stay away from using the word profits, because we're really looking at here when the cost and revenue are equal, which means your profit is $0. But 0 is not part of this coordinate here, right? You don't see a 0 up here. You see 2,500 and $1,500,000. Sometimes having too much knowledge can mess you up when you write this sentence here. Stick to what you see, what your coordinates are, and just simply putting in the units. Okay, so let's look at another similar problem. Oh, before we do that, I forgot. This is a nice visual of what we just looked at. You can see that here are the two equations, the cost equation and the revenue equation. And one line, the red line, it represents either the cost or revenue, and the blue line represents what's the other idea. So how do you know which is which? Well, remember what your equations look like. Your total cost started at, before you even made a wheelchair, 500,000. So that's your y-intercept. So this red line is your cost. This is 500,000 plus 400x. Because notice where you start, right here at $500,000. Your revenue is 600x. So that starts at the origin. You don't go into this situation making money before you even produce any wheelchairs. So the red line represents the total cost and the blue line represents the total revenue. So this question asks us, it says, fill in the boxes on the graph with the coordinates for the break-even point and the appropriate cost and revenue equations. Okay, so this box here is referring, you see the little line right here, to the cost equation. So you'd put in that box y equals 500,000 plus 400x. And this box refers to the blue line, which is y, that refers to the intersection point, which is 2,500, comma 1500000. And then this box is referring to the blue line, which is your revenue. Okay, so there are the two equations for the lines, and then your break-even point. So now the question asks us, what happens when the number of wheelchairs, which is X, is between 0 and 2,500? So that means you're looking at the portion of the graph that is below the intersection point. That's this point right here, portion right here. Notice you have the word loss here, because in this situation you see that your red line, which is your cost, your total cost, is greater than your total revenue. So what happens here is that your company is losing money because your total cost is greater than your total revenue. Right? The second question asks, what happens when the number of wheelchairs, which is represented by X, the number of wheelchairs produced and sold, is greater than 2,500? Well, that's the portion of the graph that's to the right of that intersection point. And notice the little word says gain. Well, this is a situation where your total revenue is greater than your costs, your total costs. So that means your company's making a profit. So if you're not familiar with this idea, you're not one of our business students, you may want to spend a little time with this, read the problems in the textbook, maybe do another problem. We are going to do another problem below. Just spend some time with this idea. So let's continue this idea here with a company that's going to manufacture bicycles. This company's fixed cost is much smaller. It's $100,000. It's going to cost the company $100 to produce each bicycle, and then the selling price is $300 per bike. So in this exercise, we're going to let X represent the number of bicycles produced and sold. So notice I've already defined your variable for you. So part A says to write the cost equation. So the cost equation is 100,000 plus 100x. B, the revenue equation is 300x. So we want to determine the break-even point, which is when does C equal R? So C is equal to 100,000 plus 100x, and R is equal to 300x. So when we solve this equation, we subtract 100x from each side. So we have 100,000 equals 200x. And then we divide both sides by 200, and we get x equals 500. Then to describe what that means, we use a sentence very similar to the one we used above, which says, when the company manufactures and sells 500 bicycles, the total cost and total revenue will equal, whoops, we haven't found the broke-even point. If you can't finish that sentence, you haven't found the broke-even point, because what the break-even point, because what is that break-even point? It has two coordinates. Remember, our revenue looks something like this, 300x. Our cost looks something like this. We start at 100,000 and we don't grow quite as steeply. We grow at 100x, 100 for the slope, $100 per bike, and our revenue is $300 per bike. So we have found the x coordinate for the number of bikes. We still need to find what the cost and revenue are at that point. So we're almost done. See, by writing the sentence, I realized I hadn't finished answering the question. And anytime you study something new, that's the purpose that we ask you to write the sentence, so that if you did forget the other part, that helps you to remember. So let's see, what is the total cost or what is the revenue? Well, I'm going to pick on the revenue equation because that's easier. 300 times x, in this case x is 500. So over here I do 500 times 300, 0, 0, 0, 0, 1, 5. So $150,000. So my break-even point is 500, comma 150,000. And now I interpret what each of those mean. Okay, so now I can say when the company produces and sells 500 bicycles, the total cost and revenue will both equal $150,000. Okay. The next problems ask you to write a system of linear equations in two variables, to clearly identify in words what each variable expression represent, and then interpret the results. So let's take a look at this next problem. In 2000, the combined population of Minneapolis and St. Paul, Minnesota was $670,000. The population of Minneapolis was 96,000 greater than the population of St. Paul. And this is from the Census Bureau. So it doesn't ask us to find the population of each city, but that's what they would like us to do. They'd like us in this problem to find the population of Minneapolis and the population of St. Paul in the year 2000. So we need two variables. We need a variable that's going to represent the number of people who lived in Minneapolis in 2000. And then another one, let's say S for P for St. Paul, I guess, the number of people who lived in St. Paul in 2000. All right. Now remember, to solve a system of linear equations in two variables, we need two equations. So we need to know what's equal to what. And sometimes it's a little hard to find those two what equal what's. So what do we know from the first sentence? Hopefully, as with some of the problems we looked at in the demonstration, we know a total. Like with our scholarship, we were told how much money was invested. Well, here we have the total population. Voila, there's my first what equals what. The number of people who live in Minneapolis plus the number of people who live in St. Paul in 2000 is 670,000 people. Okay, so the next equation doesn't involve interest or anything like that, but we are able to find an equation because we know something about the relationship between the number of people who live in Minneapolis and the number of people who live in St. Paul. In fact, we know that the number of people who live in Minneapolis is greater than the number of people who live in St. Paul, because it says here the population in Minneapolis is greater, 96,000 more people. So when I look at this, I say, whoops, that's not an equation. I need to come up with an equation. This is an inequality. What do I know? I know that M is representing a number of people, and that number is bigger than the number of people in St. Paul. It's bigger by 96,000 people. So how do I make these two things equal? This number M is already bigger than this number. Well, one way I could do it is to say M equals P plus 96,000. Or I could say M minus 96,000 is equal to P. In this first sentence up here, I have solved for M in terms of P. In the second equation, I have solved for P in terms of M. It doesn't matter which of these equations you use. I think the tendency is always to try to keep a plus sign if you can, at least for me it is. So I'm going to say M equals P plus 96,000. So here's my system of linear equations in two variables, and this is perfectly set up for substitution. Here is what M equals. M equals P plus 96,000. So I can take my first equation, and where I see M, I can substitute P plus 96,000 for M. So there's M plus P equals 670,000 I drop my parentheses and I get 2p plus 96,000 equals 670,000. So 2p equals 574,000 by subtracting 96,000 from both sides of the equation. And I get p equals 287,000 when I divide both sides of the equation by 2. So this tells me that there in 2000 there are 287,000 people living in St. Paul, Minnesota. And there are, okay, to find the number in Minneapolis, we've got to take this number, the 287,000, and add 9,600 to it, because we're going to find M right here. So we take P, this is P, 287,000. We're going to add 96,000 to it. And what do we come up with? Let's see, 383,000. There are 383,000 people living in Minneapolis, Minnesota. And just to be sure, I'm going to check by adding those two numbers together to make sure they equal 670,000, because I like to know that I did it correctly. And voila, it checks. Okay. So sometimes instead of instead of using two totals to come up with your system of linear equations, you're given one total, like the total population, then you're given a relationship between the two unknown quantities. All right, 4 is more standard in the sense that it involves totals of calories for certain numbers of candy bars. So what's going on here is we have Snickers bars and Reese's peanut butter cups, and we're told the total number of calories for having certain numbers of these, certain combinations, and we're asked to find the caloric content of each candy bar. Well, it's a candy bar and buttercups. All right, so let's say S is going to equal, we've got to start with our identifying our variables. For some reason I can't get my pen to work. Let's try this again. Let me stop this and see what's going on. Okay, I'm back. The pen is now working. So let's, oops, it was working. Let's try it again. Okay, so let's try this again. So let S equal the number of calories. As you can see, my pen is not working properly. Let's try, keep going here. Calories in a Snicker bar. It's not working at all. Problem solving, problem solving. Here we go. Let's try this. It's not working. All right, let's see. I'm going to shut off the video again. Okay, Math 107 students. It appears that the pen stylus has broken. I've tried orienting it, tried getting another one, but the school needs to order one. So I'm going to stop this video here. So you will see two class activity videos for lesson number 6. The first one will say exercises 1 through 3, and the next one will say exercises 4 and 5. So I will have to do that. Start board 8. So sorry I couldn't finish it all up for you. At least we got the first 3 problems.